Hi folks, and welcome back to another video of an exciting PowerPoint lesson for BCIT Technology Teacher Education, TTED5060. And today we're going to be taking a look at robot drivetrains. And I've had some experience with a number of different high school robotics competitions or educational robotics competitions. And some of the engineering or design or calculations that go into the drivetrain design for any one of those competitions is directly applicable to all of them because, really gravity and physics works the same regardless of which competition you're in. So let's go ahead and take a look at places where you can use this. Over time, the number of competitions are going to increase and change and all that. But what got me started in this was mini sumo robotics competitions where you build these little 10 centimeter by 10 centimeter robots to try and push each other out of the ring. And here's some fully autonomous tethered mini, well, they're no longer tethered now, autonomous mini sumos, but you can do tethered mini sumos with your grade 10s. This totally applies to a project you do with grade 9, 10 students. More advanced students might get into something like the VEX Robotics competition. And here you can see a robot that was competing in VEX Robotics. And you'll notice later on we're going to be talking about some of the different things about the drivetrain and the design, and you'll notice that the wheels and the flat slide are out here versus right in here we've got special type of wheel called Omni wheels that I'll be talking about later on. If you scale things up a little bit and increase your budget, get some sponsorship, you can enter the FIRST Robotics competition, and I had a lot of fun doing that when I was teaching high school at David Thompson Secondary. Here's one of our robots from Team 1346 launching itself off of one of the on-field barriers. And you can see here we've gone with an 8-wheel drive design, and we've actually rockered this a little bit. We've got these two center wheels, which are high traction wheels, lowered down just slightly more different from the end wheels, and we'll talk about why that's important to the maneuverability of this robot. And then finally, you don't actually have to do a, a an organized robotics competition. Now, international competition is really cool, but you can organize something for in your own class. And this is a project we used to do at BCIT called Vehicle in a Box, where we created our own challenge, and the students had to build a bridge this year. So they had to design their own little electric powered vehicle to come out and create the bridge. And in the process, here in particular, you'll see that this is a four-wheel drive design and with high traction wheels. It looks really good, but there's some real challenges when you go with four-wheel drive. And so we'll talk about that as we go on through the design, because there are a few tricks that if you haven't designed a robot drivetrain before, can end up catching you up. And so let's talk a little bit about some of the physics that goes into this. And then if you understand everything from first principles, then you're going to understand why some of those designs work really well and other ones have some challenges. So here is just a side view of a simplified view of a mini sumo robot. And a lot of our robots will have, especially at the simple end of things, we'll just have two wheels contacting the ground and one motor driving each wheel. You can see that we've got a design here called the BoomBot, and on each side I've got one motor, and then we've got a slidey platform up at the front. This is what the mini sumos tend to do, is because you're trying to push somebody off the ring, you want your plow to get right down underneath them. So the front of your robot will form this wedge and you want a little bit of weight resting on the plow, but you don't want too much resting on the plow because all of your pushing power is going to be transferred through your axle down through your wheel. And we're going to talk about the coefficient of friction happening right here where the wheel meets the road, actually literally where the rubber meets the road. And really important in analyzing where this goes is your center of gravity, okay, or center of mass on your robot. And you can adjust that by, when you design your robot, controlling the position of your wheel relative to the plow. You can move this forward or backwards, and where you put weights on your robot. So this is a 9-volt battery right here, and this is a 4 AA's, let's say. You could put this battery up front, and that would greatly change the position of the center of gravity of your robot, and it would greatly change the pushing and performance characteristics of this robot. So just take a moment to think about that. Where do you want your center of gravity in this robot? and you want a lot of it over top of your drive wheels, but you don't want 100% of it over top of your drive wheels, because if 100% of your weight was over top of the drive wheels, then there would be nothing keeping the plow down, and you'd go to accelerate a little bit and the plow would pop up and somebody'd be able to get in underneath you and flip you over backwards. So you need to think about this, and depending on the application that you're designing for, you're going to have different decisions in how you arrange your center of gravity and how you have mass flow through your robot into the ground. Do you want to move that wheel forward if you can? Because if you do, then you're getting more weight onto the back right here, and that's going to lever the robot back up, and it just becomes a moment question where you've got a lever arm of the amount of gravity behind, or the amount of mass behind the wheel pulling on a torque centered about this axle, and the amount of mass on this side of the axle pulling down right here. And whatever's left over, you balance it right here. Those are calculations that we did in our structures or statics class in previous semester. So take a look at your moment calculations and how those work, because they really matter here as well. Now, in addition to the center of gravity being forwards and backwards, as you get into bigger vehicles, you also need to think about your vertical center of gravity. Because although this robot's great, it's got almost all of the mass horizontally aligned right over top of the drive wheels right here at the back. And just a little bit, there's a caster down underneath right here, just a little bit from his feet and his arms, and maybe the battery that's making this whole thing run sitting right up here. But the mass of the drivers right over top of the wheels, which gave this vehicle really good performance. One of the catches, though, is that the center of gravity is mounted quite high. Generally, if you're looking at a vehicle carrying a human, you can picture the center of gravity being somewhere just above the hips. So the center of gravity is right up here. And that means that the driver, well, of course, there's inertia there. Your acceleration is happening down here at the ground. So when the axle starts to spin, it puts force through the ground. There's friction right here where the wheel meets the ground. And that means that this part of the robot starts to move forward, and this part of the robot doesn't want to move forward. And so thankfully on this one, the driver could lean forward quite a bit and move his center of gravity forward to counteract some of that torque that's happening about there. Otherwise, you'd end up having wheelies happen all the time, and the front end of the robot popping up, or the driver tipping over and falling off backwards, because when you're dealing with electric motors, you get very high rates of acceleration because you get all your torque at low RPM. Now, you also get robots that have changes in center of gravity, and here's another 1346 robot from the Robotics team at David Thompson Secondary. General Motors was kind enough to sponsor our team for several years, and here we were able to fly out to Toronto and take part in a competition at Hershey Center in Mississauga. This would have been back about 2005, 2006, I think. And here we are in the FIRST Robotics competition. And this robot actually got us onto the Discovery Channel, not for doing anything particularly well. It worked fine. It was a nice robot, and the design of the arm won us some awards. But what it got on the Discovery Channel for was that we made our center of gravity way too high on here, and you can see that there's a lot of mass right up in here. These are steel pulleys on the chain drive right in here, and we had a double reduction gearbox with big motors stuffed right in here instead of putting them down nice and low. And that was perfectly fine when our arm was down in this position and our payload was down low. But as soon as we started to raise that payload up into the air, that raising it up into the air, it's the difference between holding a bucket down here and holding it up here. When you're up in the air like that, you're really tippy back and forth, particularly if you're trying to maneuver. And our drivers really had to learn that they couldn't turn or maneuver when they had the weight all the way up in the air, because this entire robot, that's like about a 12 or 13-foot reach when it's up at the top there. The entire robot just came down, toppling down onto its side. And that was how we got our robot onto the ads on the Discovery Channel, was by having this massive tip come over there. So do watch your center of gravity and try to keep it low, because if you're lifting something up high, you really need the mass of your robot down low to allow you uh, to maneuver properly. The other thing you'll notice on this robot was that it is a four-wheel drive design, and I'll talk about some of the challenges that we run into with four-wheel drive design. And we've got high traction wheels on the front where there's actually well, depending on how the lift goes, there's different ranges of mass on there. So for instance, our center of gravity shifts not only up and down, which affects our toppling, but our center of gravity shifts forwards and backwards. So when the robot's completely unloaded, there's very little weight coming to the ground through those front wheels. It's almost all coming down from the back because the battery's right in here, the motors are all tucked right in here. And then as we pick up an object, when the arm is extended fully horizontally, the torque of that arm, the moment about the arm right there, shifts the center of gravity of the robot forward and puts a lot more weight onto the front wheel. So we get way better traction off the front wheels. At the back right here, because it's a four-wheel drive design using scrub steering or tank steering, we'll talk about this a little bit later on, but you can notice that there's zap ties around the wheels. We're doing everything that we can to try and minimize the resistance to turning and getting sideways across those wheels. At this point in our evolution as a team, we actually didn't know about omni wheels. What we had to tucked away in underneath here to help us turning, because we knew we were going to have a problem with turning, we actually had little pneumatically activated casters that would pop down and lift these rear wheels up so that we could spin the back around more easily. That also contributed to our tippiness. And so there was a lot of things that went in to this design that anyway, I'll just say we made mistakes, and I'll tell you more information about how to avoid those as we go through this presentation. So let's come back to first principles and sort of physics 11 type of things. And here we've got traction. Now, where does our traction come from? So I'm defining traction as your pushing force. Higher traction means that you can push something harder. And this is important if you're designing a mini sumo robot, because you want to be able to push someone pretty hard out of there. It also affects your acceleration. So if you want a high performing robot, you need to get a lot of traction so that you can get acceleration to push your robot forward and change your speed, okay? Now, this comes through friction of your wheel with the ground. There is what we call the normal force, okay? Normal in this sense doesn't mean in comparison to unusual. It just means normal as in perpendicular. You could call it F perpendicular if you wanted, and it's perpendicular to the surface that you're on. And in fact, it is also the force of gravity in this situation. Okay, it's only when you move onto a sloped incline or something like that where it wouldn't just be the force of gravity, and you have to start getting a bit more complex in your calculations. Now, what happens is that your normal force interacts right down here where the rubber meets the road, where the tire meets whatever surface you're driving on. And that interaction results in something that we call the coefficient of friction. And just in secret engineering code to try to keep people who haven't sat through boring lectures from understanding what's going on, instead of calling it the coefficient of friction, they've given it a nice little Greek symbol of mu. Okay, so it looks like a U, but it's got a dangly bit at the front. So, and our force of friction is a really simple calculation. I mean, in the real world, it can get really complex, but we simplify it down, and our simplified model covers about 95% of all the calculations that you're going to need to worry about. So our force of friction is equal to mu, the coefficient of friction, multiplied by our normal force. So if you know how much weight is bearing on the wheel. In other words, if you just put a scale underneath one of the wheels, you take your robot, and this is one that I was mocking up and designing, and I put batteries where I think they're going to go. I put one scale under the front right here, one scale under this wheel, and one scale under this wheel, and I could take a look at the actual forces pushing down on the robot and say, okay, I'm relatively balanced. I had about 1/3 of the weight over this wheel, 1/3 of the weight over this wheel, and 1/3 of the weight resting on the front right here. I moved things a little back to, bring this up to sort of like 40, 40, and 20, and we were doing pretty good. Um, so I know how much weight is coming down through each wheel. Okay, and we'll express that weight in newtons because it's a force. So, your scale will tell it to you in grams. And as you know, there's 10 newtons to the kilogram. So 100 grams is roughly equal to 1 newton. Okay, it's 9.8 newtons per kilogram in Earth's gravitational field. But you know what? If you say 10, I'm good with that. And so we've got this normal force coming down, and then you multiply it by our coefficient of friction, and that will tell you how hard that wheel can push forward. If you exceed the maximum force of friction that you can generate on here, your wheel's going to start to spin, or maybe you're going to start shredding the rubber, or you're going to start tearing up the surface that you're driving on. Generally, it means the wheel is going to spin or slide across the surface. Now, this also leads to a couple of situations where in your design, if you've got a low normal force, you're going to have a low force of friction. So it's really important that you get your mass over top of your drive wheels, particularly if you have non-driven wheels. So in this case, we've got two very similar robot designs. They have these drive wheels right here at the front, and then a caster at the back. And the caster is not driven, it's just there to keep everything from tipping over. And here we've got the drive wheels right up at the front as well. Now, again, when you're looking at something like this, carrying a person, so this applies to small vehicle design of all sorts of things as well. The center of mass is going to be right over top of their weight, and generally the driver's mass is huge compared to everything else in your vehicle design, if you've kept it fairly lightweight at least. And so here you can see the mass is right here, and you really can't do much to get it to move too far forward. It's coming down right here. I'd say just looking at that, almost half the weight of the driver is resting on that wheel right there. It's probably not helping them out with their maneuverability. And in fact, you can see that they've stacked their ballast up right here. They had to ballast the weight of the driver up to make the competition fair for drivers of different weights. At least they managed to put that in here fairly close to this wheel. I probably would have moved that even further forward to help shift the entire gravity forward, because those wheels could spin a little bit. Now, right in here, we also have a problem. You can see the driver's mass is sitting right back here. And in order for this vehicle to have useful performance, the driver really had to hunch up over top and shift his hips so they were up more in a position right here. And even then, he wasn't able to get it up in front far enough so that he could get good traction on these wheels. And these wheels tended to spin quite a bit. Now, not because they weren't good grippy wheels, but simply because they were trying to move a heavy force, and that heavy force that they were trying to move wasn't applying the force down through the wheels. Okay, so very important that you put your mass over top of the wheels and only leave enough on your caster right here that it doesn't allow your robot to tip over. My suggestion would be somewhere around 80% of your mass on your drive wheels, about 20% on your caster right here. A lot depends, and certainly in a situation where you have a driver on board, that mass can shift forwards and backwards depending on how the driver sits. And if you've got a robot with a big arm that doing some lifting, that mass is also going to shift forwards and backwards depending on how you've got it set up. So you always kind of want to stay within, you know, within a useful range. You certainly never want to get it to the point where this wheel has zero mass on top of it, because as soon as that gets zero mass on it, you're tipping over in the other direction. If you had another caster out right here, well, then it doesn't matter if this one's got zero, because you'll tip over that way and this one will have a couple of percent on it. But generally, mass over top of the drive wheels if you want your robot to be able to perform. And this comes to one of the benefits of all-wheel drive, and a good comparison for people who've grown up in northern BC, particularly those who've had two-wheel drive pickups. They'll appreciate the challenge of putting the mass over top of the drive wheels, because in a two-wheel drive pickup in the wintertime, you'll typically throw sandbags into the back of the pickup truck to try and weigh down the back, because you want to get the mass of the vehicle over top of those wheels to increase their interaction with the snow and the ice. Well, a better option is to go with four-wheel drive or all-wheel drive, because now all of your driving surfaces in contact with the ground are helping to propel the vehicle forward. So neither of these vehicles is going to tip over at all, but the maximum force that you can get to push this truck forward is the force normal over the rear wheel multiplied by the coefficient of friction. Whereas in this vehicle, it's the normal force of the rear wheel by its coefficient multiplied by its coefficient of friction plus the force over top of the front wheel multiplied by its coefficient of friction. And in an unloaded pickup truck, your engine block and everything up front is going to put more force over top of the front wheels. In a fully loaded pickup truck, of course, the whole point of the truck having low loading on the rear wheel is that when you put load back on here, that force goes up right back there, and you're able to move the heavy load because it's right over top of your drive wheels. Four-wheel drive, all-wheel drive, you've always got all your force over top of the drive wheels. Things also get a little bit complex if your vehicle has to climb a slope. And it's not all that common that vehicles need to climb over a slope, but you do need to think about that a little bit. Here we have a vehicle going up a slope. This created some real challenges. One of them is that, of course, now your force of friction has to be increased quite a bit, because you need to be able to get enough force to be able to push your heavy load up that hill. The other thing that happens, though, is that whereas when you're sitting vertical, your force of gravity is 100% driving down straight through from the axle straight through the contact patch of the wheel. Now you'll notice that the contact patch of the wheel is slightly ahead of the axle of the wheel. And that means that your normal force is now shifted forward to this angle right here. So you're only getting a fraction, okay, in this case, still a fairly big fraction, but you're only getting a fraction of your gravitational force coming forward as your normal force. So this reduces the amount of friction that you have acting on the robot, because you've just got less normal force. Your coefficient of friction stays the same. The other thing that starts to happen in this one is that because the center of gravity of the driver is shifted backwards, now you start to run into problems with wheelies and tipping, because now the center of mass of the driver is sitting back here behind your drive axle, whereas sitting on level ground, you're either directly above or slightly in front, and you can end up with some tipping, and you can see they've adapted for that by putting a wheelie bar on the back right here. They did make it up the hill, and it came out okay. These calculations all come into play in calculating your maximum pushing force. And oh, this was a brilliant that side of the screen. That right there was a brilliant mini sumo battle. One of the students added sparklers to their mini sumo and had a little button that used an electrical igniter, so that when they were losing the match, they could ignite it and make it look like they were being blown up as they were being pushed out of the ring. I think that was Bruce. Good job. So anyways, very memorable. So we've got these calculations right here, and they also introduce constraints. And when you know what your constraints are, then you can design within those constraints, okay? So we've got this really simple formula. The force of friction is the coefficient of friction multiplied by our normal force. We know that force equals mass times acceleration. F normal is based on the mass of your robot and the force of gravity. So you can make the robot heavier. You can shift where the center of gravity is. You can play with those things, but you're not going to be able to change the force of gravity at Earth's surface, because if you had that kind of power, well, let's just say dealing with classroom discipline probably won't be an issue for you. Uh, your maximum pushing force, therefore, is limited by the coefficient of friction between your tires and the road. And in fact, your maximum acceleration, if that's an issue for you as well, in G-force, is the coefficient of friction between your tires and the road. Um, which is an interesting thing to come about from that, particularly when you're looking at dragsters and vehicle design. All of your acceleration is built around how well can you get that traction, the force from your drive axle down onto the road. Now, just deviating from the robot side a little bit, very rarely do we worry about downforce in robots. We're not racing them tightly around corners, but since we're talking about force of friction and we're talking about tires and we're talking about downforce and how everything works together and how our robots are limited to the acceleration um, based on the coefficient of friction in their tires. Here is a Formula E race car that we saw racing in Battersea Park in London a few years ago. Really cool racing. I've been to Formula One. I've been to um, oh, anyway, I've been to a bunch of open car races, and Formula E I thought was the coolest one that I've seen so far. Everything's just so quiet. You can actually do this in developed urban areas, so you can get big crowds out to watch. And the racing is just as fast, and the cars make this amazing whistling sound as they go past. Um, so why do these race cars have all of these aerodynamics to increase their downforce? They're actually increasing their aero drag and making the car, slower in top end speed. But what that does is that adds force pushing down on the wheels without adding mass. Okay, and you can see that they try to get a lot of that over top of the rear wheels because that's where your traction drive is going into the ground, but they also need to get a bunch of it over top of the front wheels because that's where your steering's happening. And acceleration isn't just forwards and backwards in a vehicle, but it's also side to side. So in here, although the mass that they're accelerating stays the same, now their normal force is increased because they've got the force of gravity plus the downforce acting on their vehicle. Doesn't really affect your robots, but as soon as you get into talking about things like this with students, they inevitably start bringing up downforce and talking about cars because all of this stuff is really cool and it's all kind of related. Now, one of the things that also happens when you're doing this with a high school class is that they inevitably bring up Physics 11 because they have physics teachers who lie to them. Um, Much in the same way I've lied to you about Ohm's law and a number of different things, because there's always little variations that separate these things out, and we have models that simplify things. And in Physics 11, the physics teachers will tell the students that the area of contact does not matter when calculating friction, right? Now, clearly, if that were true, these guys would have much smaller wheels on here because why not? They'd be smaller, they'd be lighter, they'd be more aerodynamic. But we know that race cars have big wheels, so they come in and they say, my physics teacher told me that the amount of surface area right in here doesn't matter. The only thing that matters when you're taking a look at friction is normal force and coefficient of friction, and that tells you what your frictional force can be. Okay, it's a good model. But there's various things that are going on, and the micro level of interaction between the tire and the road, you've got a few interesting things happening in there. First of all, the road is not perfectly smooth. Okay, you've got little deviations in there, so your tire can press down into those deviations depending on how soft or sticky the tire is. The other thing that's going to be happening is as the tire starts to accelerate or go through corners, you're going to get shearing forces. And if this tire was very small, all of the force of cornering would have to come up through a very small area of the tire, and you might start to shear off some of the rubber. And in fact, you can see that happen on race cars when they leave. Well, when they literally lay rubber on the road, that means that they have exceeded the shearing force of the rubber right in here. And by having more rubber on the road, there's more surface area in order to apply that force across. So you're less likely to skid out and burn rubber. You're more likely to actually follow the path you want to go on or accelerate. So it's also kind of like saying, well, if you have cleats on your running shoes, that kind of makes a difference too. You have too many cleats, you might be too widely distributed to deform the track and have them dig in. But if you only have one cleat, it might stick in too deep, or it might shear right off, or the grass might tear when you try to use it. So the the contact patch of the wheel definitely does make a difference, but it doesn't matter for doing our normal force calculations. Okay, there is a simplified thing that we're talking about in here, and it's good enough for most of our calculations. So anyway, we've talked about a whole bunch of things outside of robotics. Let's get back to taking a look at robotics wheels right in here. And here's a few different coefficients of frictions that you might expect to get from robotics wheels. So now, if you're in the VEX competitions, VEX tends to have rubber wheels that run on a foam surface. So the foam surface deforms quite a bit, allowing you to get a pretty good coefficient of friction on there. And depending on the tire that you choose for your VEX robot, you're going to get published values of somewhere between 0.6 and 0.9. So in other words, if you've got 10 newtons of force pushing down on your axle, you're going to be able to push forwards or backwards with somewhere between 6 and 9 newtons forwards or backwards where that rubber meets the road. Now, if you've got a VEX Pro traction wheel right here, now this is, although the name is VEX again, this is a much larger wheel designed for FIRST Robotics competition. And in the FIRST Robotics competition, instead of playing on foam, you play generally on a carpeted playing field, and the deformation in the carpet and the fibers in the carpet tend to give you a lot more traction than you would expect. And you can get up to a 1.1 coefficient of friction using some of these wheels because they actually go in and they mesh with the fibers. They deform the foam underlay on the carpet, and so they can fit right in here. And you kind of get that little bit of lock and key to allow you to move forwards and backwards. And so with this, if you had 10 newtons of force pushing down on your axle and coming right down through your contact patch right down here, you would be able to push with a force of 11 newtons because 10 newtons down times 1.1. No, that's going to be good. And for our mini sumos, we cast our own polyurethane wheels, and depending on the type of polyurethane that we use, you can get it in different shore ratings for different hardnesses, depending whether you cast a smooth wheel or a bit of traction, depending on whether or not you clean the surface of the mini sumo ring to get rid of dust, whether you've cleaned your wheels to get the dust off of them. This polyurethane surface can be quite sticky, and you can get somewhere between a coefficient of friction between 1 and 2. And we can compare that to a sports car tire. On dry pavement, a typical sports car tire will have a coefficient of friction of about 1.1. Okay, so again, that limits your acceleration to about 1.1 G. However, if you've got a hot dragster tire and you've done your big burnout on a dragster, and you've got that soft rubber that you're going to basically annihilate after a couple of quarter-mile runs, you can get these tires that are sticky enough to the pavement that you can actually get up to a coefficient of friction of 5 if you're on some nice warm pavement and everything is all ready to go. So big range of coefficient of friction depending on your application. And one of the things, unless somebody's actually done some research and published values for the tires that you're using on the surface that you're using, you don't necessarily know what the coefficient of friction is going to be. So you might have to build a model and test it and calculate your own coefficient of friction so that you know how that's going to behave in other applications as well. So here's some typical questions that I might ask you about coefficient of friction. Okay, you've got a 500-gram mini sumo robot. It's got 80% of its weight on the drive wheels and a coefficient of friction between the drive wheels and the drive surface of 0.9. How hard can it push? So we just come in here and we say, well, 500 grams, that's 5 newtons in Earth's gravitational field. Okay, 5 newtons, we've got 80% of that mass is over top of the rear wheels, and you can tell that by putting a one scale under the plow and one scale under the wheels, and one should read 400 grams and one should read 100 grams. So you've got 5 newtons, 80% of it over top of the rear wheels, the drive wheels. That's 4 newtons of normal force acting on the tire, and you've got those 4 newtons pressing down, and a coefficient of friction of 0.9 means that you should be able to push that robot forward with 3.6 newtons of force. So if you were in a pushing battle with somebody whose robot had 85% of its weight on the drive wheels, okay, they would have a higher normal force. And if they had the same wheels and on the same surface have the same coefficient of friction, they should be able to push you backwards because they would have more than 3.6 newtons of pushing force. On the other hand, if you had 100% of your weight on the drive wheels, okay, that sounds like the brilliant solution. When you start pushing against someone else, now you have no weight left on your plow, and their plow has some weight left on it. And even though in ideal situations you might be able to push harder than them, if they get their plow underneath your plow, now the weight of your plow starts to push down on the front of their robot, and they start to gain some of your normal force. So they can start pushing harder and you get tipped backwards. And now your wheels aren't even touching the ground. So much for all those coefficient of friction calculations. Um, Here's one more example. FIRST robots tend to be about 120 pounds. Boo, imperial units. It's got all-wheel drive. The wheels spin at a pushing force of 100 pounds. So in other words, you take a scale, luggage scale, you tie it onto the back with a rope and you tell someone, okay, drive the robot forward as hard as you can go. And you're holding on like this, and the scale is reading 100 pounds. What's its coefficient of friction? Because the wheels will start to spin when the scale reads 100 pounds. And you say, well, I've got 100 pounds of pushing, or in this case, pulling force. That gives us 120 pounds versus 120 pounds of normal force. So we've got a 0.83 coefficient of friction before those wheels start to spin. Now, when you're pushing or pulling, friction is really good. When you're accelerating, friction is great. That's what you want. But we said that we're going to talk about some of the problems with four-wheel drive designs. And this is one that in our first year of FIRST Robotics came back and caught us really well. I understood the physics, but I'd never built a robot that size before. And anyway, I'll tell you a little bit more about that. We solved the problem with some help from other teams, but we weren't able to turn because we did a four-wheel drive skid steer robot. Okay. And most of your high school robots are going to use that because it's a very durable, reliable, straightforward way to make your robot turn. And it works like a tank or a bulldozer in order to make the robot turn in this direction, you drive these wheels forward and you drive these wheels backwards, and the robot ends up developing a desire to twist. Now, in order for it to twist, okay, for the robot to turn this way, you need to overcome scrub torque. And that means that this wheel needs to break free in a horizontal direction and skid to the side. That's why it's called skid steering. If you've got really good forwards and backwards traction, that's great. But if you've got really good side-to-side traction, you're going to be stuck there because your forwards and backwards traction that are trying to turn the robot this way are going to be fighting against your resistance to the lateral forces. And so you're going to have to overcome the torque of your scrub torque right here. Now, this robot can probably do it because you'll notice that the distance from the turning point right here, the center of the robot, out to the drivetrains, okay, is about the same distance right here as it is right in here. In fact, it's considerably longer coming out here when I look at that, when I look at the contact points right here. The contact point over here is a fairly good horizontal distance, while in here this is a fairly short vertical distance right on here. That means that your moment arm that's pushing the robot forward and pulling the robot backwards is greater than the scrub that you're overcoming. Now, that's why this design would probably turn. However, if you picture this being a longer robot, okay, a rectangular shape that comes out to, right up here somewhere. Okay, now your turning point is going to be somewhere in the middle, and you're going to have this long lever arm back to where your axles meet meet the road, and that's going to increase the lever arm coming back that way, and the lever arm back over here is going to be greater than your lever arm to your sides that are trying to push you forwards and backwards. You're going to have a real hard time turning. And what happened to us with our very first robot at David Thompson is we built it with four-wheel drive. It was probably about this kind of rectangle, and it turned great in the shop. We had four high traction wheels, front and back, big wheels that we picked up, big heavy things that we never ever used again, pneumatic wheels that we picked up at Princess Auto. And anyway, in our shop on the cement floors, the robot spun beautifully. When we got to the competition, we'd never actually tested it on carpet until that point. We put it on the carpet. Well, the carpet, the coefficient of friction went up considerably. And although that was great for how hard we could push and how hard we could accelerate and how well we moved forwards and backwards, it was terrible for our turning because the scrub torque went up so high that in order for our wheels to overcome it, they actually twisted the chassis of our robot to go bump, 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 bump. And anyway, the robot was very unstable in turning, and we couldn't get a smooth turn to save our life. Robot worked beautiful on a low friction surface, completely screwed up on a high friction surface. So we'll take a look at some of the things you can put into your design to overcome that, because as we learned over the years, those problems got solved. Here are some skid steer solutions that we've used in a number of different places. And so with our tethered robots, well, we'll completely ignore the problem because what we'll do is we'll have two drive wheels, and then we'll just have a contact patch right here that has very, very low coefficient of friction because it's just going to be a little slider that fits right in there. And so it's got no forwards and back, minimal forwards and backwards, and minimal side to side friction. So that's going to slide very nicely from side to side. Right in here, we've got the boom bot, and my head's kind of sitting over top of the wheels right here, but we're also going to make a boom bot. Down here, we've got our line following sensors. And again, they are going to be in a low friction skid platform. So that's only there to keep the robot from tipping over forwards and backwards and to follow the lines. It's got very little interference with turning side to side, so very little scrub torque. Here's a vehicle that we made for the Vehicle in a Box contest, and you can see that it's got casters on here. So when this wheel turns forward and the one on that side turns backwards, it generates a turning torque right here, and the casters will turn and allow it, the front of the robot to skid. Yeah, that works as well. They're probably the most inexpensive option to solving this problem. Putting a skid surface down here wouldn't work that well. We'd scratch up the floor something horrifically. So we needed something that was wheeled to solve the problem, and casters are readily available, either from a place like Casterland or from recycling old office chairs or furniture or something like that. You'll notice that there are some really good aspects to the design on this robot. Look where that center of mass is, right over here. And in fact, some of the heavy parts are actually on the back of the axle, which shifts the center of gravity backwards even a little bit further. And I wouldn't be surprised if the driver leans back on this one, that they actually run the risk of popping a wheelie sometimes. Now, for the first robots where you don't have a driver on board, here's a couple of solutions that will work as well. I talked about going with the six-wheel drive or eight-wheel drive type systems where you put the center wheel or wheels a little bit lower than the front and back axles. And what that does is that means that at any one point, you can only have these two or these two in firm contact with the ground. So if your mass is sitting a little heavier back here, these two wheels are in contact. And if the load shifts at some point or you're decelerating and it shifts over here, well, then these two are in contact. And what that allows you to do is that greatly reduces that forwards and backwards distance, reducing the lever arm and allowing the robot to spin more easily. These guys have also put on something called an omni wheel, and an omni wheel is specifically designed to deal with the lateral turning resistance. And you can see it's got rollers right on here, and these rollers go all the way around the wheel. So you've got beautiful forwards and backwards coefficient of friction, because these are nice soft rubber rollers, but they will roll side to side. So when you go to turn, they can spin in this direction. And these are, I'd say, the the concept is kind of like a caster, but they behave a lot better, and they make it really easy to make these into driven wheels. So right here and here in this design, there's probably a belt that comes out and drives the front and back wheel. I think you can see the belts coming down right in here, and that can help increase your overall pushing ability. So there's some really neat stuff going on in robot designs. There's a couple of good books on FIRST Robotics called FIRST Robotics Behind the Design that they've been out of print for a little while now, but you can find them in public libraries and academic libraries. Definitely worth taking a look through there. And you can see all sorts of interesting solutions to skid steer and how to design a robot drivetrain. Now, getting back to some calculations on here, and the calculations that you're going to be doing for me is we're going to take a look at the moment about the drive axle. Well, what do I mean about that? Everything in your robot is going to be controlled by spinning an axle. So the torque about the drive axle is simply the force acting at the edge of the tire multiplied by the radius of the tire. Okay, so this torque right in here in purple, or the moment if you prefer, is going to be 5 newtons multiplied by 15 millimeters, or 75 newton millimeters. Keep in mind Newton millimeters, you'll sometimes see that represented as millinewton meters. Doesn't really matter where you put the milli, okay? Either way, it comes out to 0.075 Newton meters because milli is 3 decimal places. So 1 decimal place, 2 decimal places, 3 decimal places. There's our 75 millinewton meters, the same as 1, 2, 3.075 Newton meters. Excuse me, I hope I managed to get mute turned on before. Okay, now if the force at the edge of this wheel exceeds the force of traction, the wheel begins to spin and you do a burnout. Generally, we're going to come up with two situations on here. One is where you have the wheel break free and you do a burnout. And the other is where the coefficient of friction is high enough that you don't have enough torque in your axle coming from your motors, and you end up stalling the motors. So we can either stall or spin depending on the amount of torque that we're getting from our motor and our gearbox. And we're going to take a look at how to optimize that in a little bit. Now, your tire or wheel diameter really matters in here, okay? As you increase the wheel diameter, you increase this lever arm right here. And what that does is that increases the amount of torque that's required to turn this wheel. So with a small diameter wheel, okay, or small radius, we're using the radius as the lever arm right here, 5 newtons at this point right here of pushing power, or pushing force, I should be more clear, 5 newtons times 15 gave us 75 millinewton meters. But if we go with a larger diameter wheel, right here with a 30 millimeter radius, well, that's going to require 150 Newton millimeters to turn this wheel to get 5 newtons right down here. So if these two robots are in a pushing battle, this one right here is only going to need half of the force coming from the half of the torque at the axle coming from the motors and the gearbox. Okay. The advantage, of course, of the larger wheel is that when this axle and this axle spin at the same RPM, this robot will travel twice as fast because if this robot's spinning at 100 RPM, you've got 100 circumferences of this wheel in every minute. And with this one spinning at 100 RPM, you'd only have 100 circumferences of this wheel every minute. And this wheel has half the circumference because it's got half the radius. So your tire diameter, your wheel diameter really does make a difference. Now, again, when you look at that right there, uh, our torque to spin that wheel has to come from somewhere. It comes from our motors and our gears. And we've got a video where we talk about motors and their maximum output torque. And generally what we want to do is we want to take a small motor like this one right here, and then run it through this yellow gearbox right here to increase the amount of torque and drop the RPM so that we can spin a larger diameter wheel. Because if we just hooked this wheel directly up to this motor, the motor wouldn't have enough torque to turn the wheel, and it would just sit there and it would be continuously stalled. Um, so uh, for instance, right in here, if a motor has 1 millinewton meter of torque and a 100 to 1 gear reduction, then the torque at the axle would be 1 millinewton meters times the 100-fold gear reduction, which gives us 100 millinewton meters at the axle. Okay, now that would be enough to turn this wheel, because we did a calculation and said that this wheel, to get 5 newtons of pushing force, would only need 75 Newton millimeters. This one would require 150 Newton millimeters. So this particular gearbox right here with a 1 millinewton meter motor, millinewton meter motor, and a 100 to 1 reduction would be able to make this robot push with 5 newtons of force, but would not be able to make this robot push with 5 newtons of force. On the other hand, this robot down here would move faster, okay, because your RPM is also being reduced 100 to 1. That's where you're getting the extra torque from. Now, when we look at it from the side and do all our calculations coming from one side, we forget sometimes that there's two motors acting in here. So, really we can divide by 2 or multiply the motor force by 2 just to do the overall calculations. So here's an example of a typical question that you'd find if you're trying to design a robot. And here I'm going to use an FRC robot, but this applies to putting a electric drivetrain underneath a lazy boy chair. Okay, because why not? If you want to do hallway patrol or run something down to the office, why not put a little robot like this underneath the chair and have it scoot you down to the office? Okay, this applies if you're making mini sumo robots, if you're making something mid-range like the Boombot, if you're designing VEX robots. This is an FRC robot, but the calculations are common to all of them. You just sub in different motors and different gear reductions and different wheel diameters. The math is all the same. So we're using 2 CIM motors on each side. So on this robot, we've got 2 motors driving a gearbox right here and 2 motors driving a gearbox right over here. Okay, each gearbox has a 14 to 1 gear reduction. The sim motor has a stall torque of 2.42 Newton meters. So in other words, when you apply 12 volts to that motor, it's going to turn the motor shaft with a maximum of 2.42 Newton meters of torque. Okay, you've got an all-wheel drive drivetrain right here, so the entire mass of the robot is coming into the ground, and you have 15 centimeter diameter wheels. What's the maximum pushing force that your motors can achieve? Okay, how hard can you push? Well, we've got on one side of the robot, okay, we've got 2.42 Newton meters from each motor. We've got 2 motors on each side, okay, and we've got a 14 to 1 gear reduction. So that's going to give us 67.8 Newton meters coming out of the gearbox at the axle shaft coming out of the gearbox. That is going to be hooked up, and we've actually got a chain drive in here connecting to all the wheels. Because the wheels are all the same diameter, it's perfectly fine. We don't have to do any further calculations. We've got a 0.075 meter radius. Okay. Now keep in mind I said they're 15 centimeters in diameter. That means 7.5 centimeters in radius. So 7.5 centimeters is 0.075 meters. Let's keep it all in terms of Newton meters here so we don't start getting millimeters in the way. That's going to give us 903 newtons of force acting on this side of the drivetrain. We've got 2 sets of drive wheels on there. That's going to give us 1,800 newtons of pushing force, or approximately 180 kilograms of pushing force. That's pretty good. Where did some of these uh, numbers come from? Well, these numbers are published on the motor curve, motor power curve, and we've got a video where we talk about that as well. Um, Two motors, well, that was part of the design. We've got you know, our 14-to-1 gear reduction. You could change that gear reduction. So if this is way too much force, you could go to a lower gear reduction and maybe get a robot that moves faster. Or you could go to a larger diameter wheel and get a robot that can't push quite as hard but moves a little bit faster. So then we'll hit that with a follow-up question and say, if the robot has a mass of 60 kilograms and a coefficient of friction of 1.1, between the wheels and the playing field, do the wheels spin or does the motor stall when you're turning that motor at maximum torque? Okay, so what we can do is we can say, well, 60 kilograms times 10 newtons per kilogram means that the entire mass of the robot has a normal force of 600 newtons. Our 600 newtons normal force multiplied by the coefficient of friction is 1.1. So our coefficient of friction results in an absolute maximum pushing force of 660 newtons. Well, we just did a calculation saying that our motors could achieve a pushing force of 1,800 newtons. But when that goes down through the wheels, our traction limit is 660 newtons. So what's going to happen under this situation is that your wheels will spin, okay, and break free and sit there and burn rubber before those motors stall. So really, you could make this machine a little faster. You could make bigger wheels. You could go to lower gear reduction. But as you'll see when we take a look at the motor power curve, sometimes that's a really nice way to have it because that means that during normal driving operations, your motors are operating in a more efficient RPM range. So as you want to get more pushing force out of your robot, and as you increase that gear reduction ratio, you reduce the speed of your output shaft. Lets you turn that output shaft harder, but you reduce your peak speed. Now the trade-off at the other end is as you increase your wheel diameter, you increase the speed of your robot, gaining speed but reducing the maximum pushing force that your motors can generate. So when you're designing your robot, you're going to have to do some calculations and figure out how big a wheel do you want, and based on the size of the wheel and how hard you want that robot to be able to push, you need to then take that back and say, well, what force do I need about the drive axle? Figure out your gear ratios based on the performance characteristics of your motor. So here's one to take a look at your Tethered Mini Sumo robots because this affects your speed calculations as well. Your Tethered Mini Sumo robot achieves a maximum motor power output at a speed of 6,113 RPM. And again, there's another presentation that looks at motor power curves that will talk about that. Typically, we might have a 1-inch, 25-millimeter diameter wheel on a Tethered Mini Sumo robot, and one of the gear reduction options that you can build into a Tamiya gearbox is 114.7 to 1. There's a handout called Mini Sumo Design Tips that discusses the different gear ratios and suggests some different wheel diameters that you might want to try and walks you through some of these calculations step by step. So what is the peak velocity of your robot going to be under this setting? So if you're achieving your peak velocity at your peak power, so you take your 6,113 RPM, that's what your little motor in here, right there, the little motor itself is going to be spinning at 6,000 RPM. Divide that by 114.7, which is your gear reduction ratio, and that means that your axle shaft should be turning at 53.3 RPM. Okay, and now you can say, well, 53.3 RPM. We know there's 60 seconds in a minute. Let's get this down to seconds. Okay, so we're getting 0.8 revolutions per second at the axle. We know our wheel circumference, so the distance around our wheel, we're talking about a 1-inch diameter, 25 millimeter diameter wheel right here, is pi d. So pi times the diameter of our wheel gives us 78.5 millimeters of circumference all around that wheel. That means that our axle spins 0.8 times per second, and each time it spins, you move 78.5 millimeters forward. So 78.5 millimeters, the wheel circumference multiplied by the speed of the axle shaft in revolutions per second, tells you that the robot will move at 69 millimeters per second. And, you know, for a tethered mini sumo, that's just about right. You'll see, like I say in the handout on tethered mini sumo design tips, that we say sometimes you can actually build a tethered mini sumo that moves too fast and it's difficult to control, let alone not having very much pushing power. You do need to be able to control these robots, and sometimes one of the reasons we gear the motors down is just to make them more controllable. Now, as I was saying, this is applicable to robots, and we're discussing it in the context of mini sumo robots, these little things that you can hold in your hand. But really, they apply to anywhere where you're using any kind of motor to build any kind of vehicle. And one of the first projects I did when I started teaching high school and was fresh out of BCIT was we made electrothon race cars. And this wasn't our first one. You can see it's actually got some cedar strips left over. One of the woodwork projects going on in the wood shop was building a cedar strip canoe, and they had a bunch of these cedar strips left over. So we used cedar strip canoe building technique to build a fiberglass chassis for our electrothon race car, and this really performed nicely. And one of the reasons it performed nicely is because we took a look at the performance characteristics on the motor curve, and you can see right back here, we very carefully chose a drive pulley system and a tooth coming off the number of teeth on our main gear to hook this up so that we would be able to drive a wheel of this diameter in our peak efficiency range for our race. So being able to understand how the force goes down to the ground really does affect your ability to design a useful vehicle. The other thing that we paid a lot of attention to with this being a tricycle design was making sure that the center of gravity was well within the triangle defined by the wheels so that it would not be a particularly tippy tricycle. We put our batteries right up here at the front, so that shifted the center of gravity forward and also helped our ability to steer when we came into the corner, because this vehicle was never going to be involved in high speed acceleration or in a pushing contest. We weren't too worried about getting too much force over top of the rear wheel. With the driver's butt being right down about here, there was plenty of force on the rear wheel. With the batteries up front, we actually had pretty close to a nice 1/3, 1/3, 1/3 distribution of force into the drive wheels or into the wheels there, which resulted in fairly nice handling. And although this wasn't the fastest electrothon car on the track, it was kind of top 2 or top 3 in BC that year. It was definitely the most maneuverable, and if there'd been a slalom competition, I'm pretty sure this one would have ended up winning. Now, when we were working with that, we had to play around with our gearing to try and get it optimal, and we ended up doing lots of test runs. But we used the power curve to figure this out because we wanted to run our robot really close to our peak efficiency, or run our vehicle pretty close to our peak efficiency range down here. And that involved working with the drive wheel diameter and the pulley ratios, which were our equivalent of a gearbox on this system, to make it all come together well. We'll talk more about the power curves later. Right. So what gearboxes do we have available for you for making a tethered mini sumo robot? There's these little yellow gearboxes have become an option in recent year. You'll sometimes see them called a toy car gearbox or a TT gearbox. You can find them online from a number of different vendors, and you'll require 2 of those. They're a couple of dollars a piece. Downside or upside, depending on how you look at it, is you don't actually assemble them, they come pre-assembled. The gearboxes that I've been using for, I was going to say years, for decades with my students now are the Tamiya twin gearboxes. And they're available from a number of online vendors. My suggestion for buying them in Canada is the same place I've been buying them bulk for years is Borgfeld, BORGFELDT.ca. And in fact, yeah, excuse me, you have to phone them actually is the best way to get the best deal on that. They do have an online site, but you order them 50 per box when you're ordering them for your class, and you'll get a way better rate than I've been able to find anywhere else on the Tamiya gearboxes. Now, what's neat about the Tamiya gearboxes is that they come in pieces and your students actually assemble them, and because they're assembling them, they can choose their gear ratios. So anyway, with the twin motor gearbox, you get a choice of 58 to 1. So 58 revolutions of the motor give you 1 revolution of the output shaft. So a high-speed gearbox, or 203 to 1, which is usually my favorite setup. And in that case, the axle comes out of this hole right here. And that means that for 203 revolutions of each motor, then you end up getting 1 revolution your output shaft. So the output shaft is 4 times as slow at 203 to 1, but 4 times as torquey. A while ago, I also started bringing in the Tamiya dual motor gearbox, and physically this gearbox is a little bit wider and a little bit shorter than the twin motor gearbox. They're very similar in their design and how they work. They're both a two-stage gear reduction, just a few different choices of gears on here. And this one looks like it offers more choices. 12.7 to 1 is really useless for tethered mini sumo design. These motors are so low torque that and spin so fast that 12.7 to 1 doesn't gear them down enough to actually drive your robot. So that's really not a meaningful option. Even 38 to 1 is that's a really fast robot. You'd want to do that with a fairly small diameter wheel, and you might still run into some control problems. 114.7 to 1 is a really good ratio for small to medium diameter wheels. Performs fairly similar to the 203 to 1 right in here. The 344.2 can be really slow unless you have a large diameter wheel on your robot. Because keep in mind, that means that for every 344 revolutions that this motor does, you get 1 revolution coming out right here. So that'll give you a lot of pushing force, probably a lot more than your coefficient of friction can actually manage. But that wheel is going to be spinning fairly slow. So unless you have a fairly large diameter wheel on there, you're going to have a very slow robot, and somebody will probably sneak around to the back of your robot instead of pushing on your plow that you've designed to do all your pushing. Somebody with a faster robot will get in behind you and attack you from your weak spots. So we've got a few different choices. Again, if you had to just choose one for your classes, this Tamiya works pretty good. Or choose this one, just don't build the 12.7 to 1. It doesn't work well for our applications. Now, the nice thing about this is we do know performance characteristics of the motors, and what's interesting is that you can actually swap out the motors. There are motors of similar size but with different windings that have different performance characteristics. So if you hunt around either on the TT gearboxes or on the Tamiya gearboxes, intrepid minds can actually supercharge their machine by upgrading the motors to better match the batteries that we've got. I'm not going to tell you any more about that aside from saying it is possible. I have had students go out there and do it. And I've smiled and nodded because I've known what they've done. And we haven't mentioned anything to the other students until it was all over and done with. And it was like, hey, they went out and did the research. I didn't say you couldn't use a different motor. So anyway, if I don't say you can't use a different motor, then doing your research and figuring it out is probably a really good idea. We've got the motor power curve in here. Again, we'll talk about motor power curves in a different video. And this is the spec, as far as I can tell, it is on the motors that we're using. And you'll see, again, I've written about this a fair bit in the Tethered Mini Sumo design tips, and put them up on the Bot Shop WordPress site. In fact, you should be able to just Google Tethered Mini Sumo and have most of my stuff come up. I've been somewhere near #1 on Google for the last decade or so on Tethered Mini Sumo, kind of niche area to be uh, in. Okay, now your Mini Sumo can have a wide range of interpretations. There are some rules, however. In your starting position, when you begin your tethered mini sumo battle, you have to be within a vertical column that is 100 millimeters by 100 millimeters. You can be unlimited height. I don't care how high it is when you start, but you can't touch it to tip it over. Okay, so this robot right here, clearly more than 100 millimeters long. But when it starts rotated upwards, and this wheel right here at the back, they went with a slightly larger wheel, is touching the ground so that when they tap their controller in reverse, the wheel spins backwards, this kicks out, and the top falls down, and now the robot's got this nice smooth plow coming right along like that. Really beautiful looking robot. And it worked pretty well too. It was fairly competitive. That plow really did get underneath other people, but beautiful artwork on there. The woman who designed this did a really nice job. Um, some robots people will sometimes get into art robots, and yeah, this robot got his butt kicked all over the place in terms of competition. But how do you give a bad mark to such a beautiful interpretation of a Dalek? Anyways, we had a good time with this one, and a lot of work went into designing that. Over here, we had another one where somebody thought, oh, I've got it figured out, and missed one little part of physics. Okay, now they were right about the fact that, they start with these arms folded up. They're all within the 100 millimeter by 100 millimeter vertical box. They spin the robot, and these drop down, and the robot sits there and it spins around. The idea being that these arms will knock their opponents off the playing field. The catch is they forgot to calculate the lever arm from their drive axle out to here where they're intersecting with the other robot, and the other robot's out here with a very short lever arm from its perspective, and it's able to push and spin this guy around all at once because these arms are so long. It'd be like trying to fight someone with your arms out like this and whapping them on the side of the head. You don't do that. You kind of stay in a little bit closer. Um, Let's see, other rules that you're going to have in your robot design, maximum of 500 grams mass. Now, just as it doesn't make sense to build or design for a 100 millimeter by 100 millimeter robot, don't build it to 100 millimeters by 100 millimeters because I've got a testing box, and if you're 1 millimeter over, I start taking marks off, and if you're 5 millimeters over, you got to go back and do it all over again. I should just rule you out if you're over 100 millimeters and say, no, I told you 100 millimeters. But I don't know, I've got a soft spot in my heart somewhere, maybe in my head. Anyway, your robot may expand after starting, maximum of 500 grams, not 501 grams. If you're 501 grams, you lose a mark. Okay, 500 even, you're fine. 497, perfect. 501, not so good. Keep in mind that different batteries have different weights. So if you change your batteries and go to a different brand of batteries and gain 3 grams and you built your robot to be 499, now you're at 502 and you've got an illegal robot. For our rules, you must run on a 4xAA alkaline battery pack, okay, and the batteries must be on board the robot. You also have to be able to change those batteries fairly quickly. You have to use one of the gearboxes supplied, okay, which is generally not a problem for people. We've got a nice range of gearboxes to choose from. And your batteries, weights, and other unsightly objects must be concealed. Generally, we will want to add some ballast weights because the combination of your motors and gearbox, robot chassis, wheels, and batteries usually comes in somewhere between 200 and 300 grams. So if you add a few extra weights to your robot, then you can bring it up and make it a little beefier for pushing other people around because, of course, you increase that normal force, which increases your maximum pushing force. But they need to be hidden away nicely. And just to be clear, visible tape or hot glue on the outside of the robot are considered unsightly. We want to do a nice job of our design. You'll also see that we've started adding 10 centimeter tether poles on here, basically a welding rod that come up off of the chassis, and those will have to be firmly attached to your chassis, and you'll take your tether wire and run it up that pole so that you're not getting your wires caught with somebody else when you're out there driving the robot around. So you've got to have that little 10 centimeter tether pole coming up to control your robot. Here's some examples of different tethered mini sumo robot designs that we've seen. This one, I seem to recall, did very well in competition. I think it may have won that year. It lost marks for visible hot glue and visible batteries, but it was very competitive. And you'll notice that it's got a plow right down here that fits very flush to the ground. So when this one got into pushing battles, it was very hard for people to get underneath there and lift the front up. In fact, he'd get underneath other people and lift their front up on there. This one, just an example of how you can add some graphics to your robot here. And here's an example of how, if you're going to add ballast weight, you can do it and keep it looking relatively nice. Put a bit of spray paint onto your ballast in there and make it look like part of your robot instead of just a big ugly weight. Some other creative things that we've got right in here, a little bit of paint goes a long way to making your robot look pretty good. This one ran into a few problems right here. It needed some side panels right in here. You can see the batteries kind of dangling out to the side. The front is beautiful, sides, not so much. But anyway, hey, it's a first robot design, and it's nice to see the creativity coming in right there and a bit of personality in the robots. Here you can see a range of different control boards, and we'll talk more about the control boards and how we drive the motors in a later presentation. But you can see some fairly standard designs, but also some interesting approaches on putting things together. Now, I've shown you a bunch of metal robots. That was how I built them with my students. I did this in a robotics and flight grade 9 and 10 introductory tech class. Students do their little rotation through the grade 8 classes here in BC, get a taste for it. Maybe they come back and do the class with me. I was teaching in Vancouver, so selling a course as metalwork wasn't a big sale to a lot of parents, but selling it as robotics and flight was, and the kids could sign up for a shop class. And it also brought a different part of the school down into the shop classes because, hey, I'm coming down for robotics and flight, and Mr. Brett's going to talk about some of the physics that go into designing the robot, and friction, and gear ratios, and batteries, and current. And it became a really general tech course. And in the whole process, I ended up using it as an example to teach sheet metal work. I had the students turn wheels on the lathe, and we covered a lot of classic metalworking skills that you do with a grade 9 or 10 student. We drilled and tapped set screws to hold our aluminum wheels onto the axle shaft, and I was really pleased with how I was selling grade 9 metalwork as a robotics course. But maybe you're teaching drafting, or maybe you don't have sheet metal tools in your shop, or maybe you're just interested in doing this project. You can do it in any shop. You could make these out of wood if you wanted. But if you're doing it in a CAD lab, well, why not 3D print your designs? And these are some of the 3D printed designs that students have developed. And you can see that they got into Inventor or Fusion 360 or whatever CAD program they wanted to use, and ended up coming up with some really nice designs that they kicked out on the 3D printers. And what's really neat about doing it that way is, of course, you can download the models for the Tamiya gearbox and for the battery pack, so you can actually use them in your virtual world inside your computer to make sure that you're not getting any intersections with things, or building things that can't be done. You can actually have a really nice working model all set up and ready to go. Here we go. We've got some graphics on there. I always love a piece symbol. We use the vinyl cutter on here, and the student decorated that up nicely, or maybe they just bought some stickers. A little bit of extra weight on here. Not quite sure whether the bearing was intended with evil intent to help push people out of the ring, but you'll notice this one has a really large diameter wheel on it. So that means that the gearbox probably has really large gear reduction. The other thing you run into when you've got really large diameter wheels is that you have to move the axle shaft forward from the rear wall of the robot simply so that you can fit the wheel into your 10 centimeter by 10 centimeter allocation. Uh, Here's another one, medium-sized wheel. This person chose to go with a hexagonal wheel, but they kind of, or maybe octagonal, but they flatten the corners down a little bit here. Tire smoothed everything out nicely, and it worked pretty good. And a couple examples of sheet metal design right in here. Not the nicest job of folding I've ever seen. And here's a CAD model coming together showing that the battery pack is going to fit inside the box. And in fact, you can design it in CAD, and if you're using Inventor Fusion 360, they have sheet metal tools. You don't necessarily need to design the entire thing in to be 3D printed because you can use sheet metal as well. Now, I've got another set of videos that show how I actually use good old pencil and paper to design an orthographic view of the robot and use that to develop the layout view because that's what I had my students do in high school. We weren't in a computer lab. We didn't have computers for everyone to use. And, that's quite common situation in some of the shop classes. And honestly, it's not bad for students to learn how to use a couple of squares to create a nice orthographic drawing and draw a layout extract a layout drawing from that. Like I say, teaching robotics. I've got some electronics in there. I've got some metalworking in there. You can bring this together. And the beautiful thing about robotics and why I think it's such a great tech ed project is that it brings all sorts of disciplines together. It brings your design and drawing. It brings metalwork if you want. It can bring 3D printing if you want. It's got electronics in there, and it's got a strong backing of physics, which when you start teaching that, starts to attract other students into your classes who maybe don't normally sign up for tech studies courses. Anyway, there we go. Like I say, there's two documents that follow up on this. They're available if you're just watching this on YouTube. You can go to botshop.wordpress.com and you'll find the documents there under Tethered Mini Sumo. Just Google Tethered Mini Sumo and you'll come to the site as well as some video of my students engaged in Mini Sumo competition. And if you're doing this as part of your course at BCIT, I'll have that information up on D2L as well. Alrighty, have a good one and enjoy designing your Tethered Mini Sumo robot. Remember to start by figuring out what gear ratio you want, what gearbox you're using, what diameter wheel you're using, and when you've got that part figured out, then you can go on to where I talk about creating the orthographic drawing of your robot and extracting the sheet metal design.